whenever you have any kind of word problem related to what we call optimization, so finding maximum and minimum values, you have to include the first derivative test, or when we learn about the second derivative test, to verify that your extreme value is in fact a maximum rather than a minimum, or a minimum rather than a maximum. All right, so that's the motivation here. It's checking the box, you know. So because if you have a calculator, if you have technology available to you, you verify analytically that there is an extreme value at, let's say, x equals 2. Then you look on the picture and you see that it's clearly a maximum there. And you're like, why do I have to do any of this other stuff? They want you to show it all analytically. All right, so that's the motivation behind it. All right, it's very flimsy though. All right, so tell where x cubed plus 2 is increasing, decreasing, and identify any relative extrema. Now again, we talked about this yesterday. If I know, maybe the day before, I'm not sure. You know what a cube function, a cubic function looks like, then you already have a sense of where it's increasing, possibly decreasing, any turning points that might exist. So you have an idea. It's just a question of fleshing out exactly where they would be. All right, so the first thing we're going to do is address continuity and differentiability. Okay, I have addressed it. All right. On the AP, you would write because it's a polynomial function, and polynomial functions are always continuous and differentiable for all values of x. Yeah, the whole shebang. Whole shebang, yeah. Yes. Yeah, you gotta love them. All right. Now, if you're doing it for your own purposes, you're not going to make the statement, but you are going to consider continuity and differentiability. You're going to say to yourself, oh, are there any asymptotes? Are there any points where the function doesn't exist? Because if I go through the process of finding a critical point and I get, let's say, x equals 2, but that coincides with a vertical asymptote, then I would know to disregard that x equals 2. All right? So for your own benefit, it's valuable. Just all the extra stuff that you have to write is annoying. All right? So I could take my derivative. It's an unbounded function. So it's not a case where Rolle's theorem would apply, so I don't have to test any endpoints. So the unfortunate thing is if you have a bounded interval and you test the endpoints, and it turns out the endpoints have the same height, then you would know without doing any more work that there has to be some turning point, or at least some point where the function has the derivative equal to 0 in there, making it a worthwhile endeavor to take the derivative, set it equal to 0, and solve. All right? In this case, it's not a big deal to do it, but if I gave you some monstrous function, you may want to kind of vet it out first, make a determination of whether it's worth doing all that work before you start doing all that work. All right? So 0 would be equal to 3x squared, and that would make x equal to 0. That's my critical value. All right? Not necessarily a relative extremum. All right? That's the thing. Critical value is not necessarily a relative extremum. A relative extremum must be a critical value. So if you already know something is a relative extremum, a max or a min, then the x value coinciding with that must have come from your set of critical values, but not all critical values will lead to relative extrema. All right? So the converse relationship is not always true. So what I'm going to do is create a sign chart that compares the x values.
Do we have to do like 3x squared equals 1 over 0? And then plus it out?
I should have done that, yeah. Very good, thank you. All right, so our sign chart would have the x values, the f prime values, and some kind of conclusion. All right, the conclusion is going to vary, obviously, depending on where we are in the domain. All right, so this is the tedious part.
No.
Maybe I just make it tedious by saying it's going to be tedious. I think it's actually really enjoyable.
Now every time I'll do it, I'll think
Yeah.
those two, like that third?
Wide, skinny Y.
Okay.
Yeah.
That's right. Yeah.
All right. And the reason why I would know that going in, and you'll get experience with it, but I have one critical value, so I'm going to have an interval to the left of the critical value, and then an interval to the right. So if I had two critical values, I'd have interval, critical value, interval, critical value, interval. All right. So it's always going to have that same stuff. I have to account for all possible values of x on the domain. So negative infinity to 0, but not including the 0, because 0 is going to be all by its lonesome in the middle of that column. Lonely 0. And then 0 on to infinity. All right, so it's related to the domain. It's not exactly the domain. All right, not necessarily anyway. Sometimes it coincides precisely, sometimes not quite. The good news is I don't need numerical values. It's called the sign chart for a reason. I just need the sign of the derivative. All right, so SIGN, the positive or negative. So if I plug a number from this interval into my derivative function, what kind of number will I get as a result? Positive. All right, and that's because I'm squaring a number. You square a number makes a positive, and I'm multiplying a positive by a positive, result will be positive. If I take an interval in this set of natural numbers over here, well, actually not really natural numbers because it could also account for radicals and other kind of rationals. But if I take a positive number and plug it into my derivative function, what kind of number will I get as a result? Positive. All right. If a derivative is positive, that means that the slope of the function at that point is positive. All right, which means that the function itself is increasing. All right. So, what does that tell us? Because our directions here are telling us to make a determination of whether it's increasing, decreasing, and/or decreasing, and make a determination if there's any relative extrema. So it looks like it's increasing throughout. We know that the slope is equal to 0 at 0, right? Well, I pointed to the 0, but the slope is actually 0 at 0 because we set the derivative function equal to 0 and solved, all right? The conclusion that we would draw is that there is no extreme value here, so no relative extrema. So let's take a look at it graphically so we can get a sense of why that might be the case. First off, if you have an idea of what a cubic function looks like, you might already know. And I drew one out, I think it was yesterday, but I'm not really 100% sure. So cubic functions could look like this. They could look like this. They can just flat out level off. And then one other possibility really would be the reverse of that where it's increasing. All right. So you have really these four variations of it, you know, with varying amounts of stretch and skew and things like that. All right. So in this case, I would have two critical values. I'd have a relative max, a relative min. Actually, in both of these cases. All right. This one would be increasing, then decreasing, then increasing again. All right. That didn't happen here. This one would be decreasing, then increasing, then decreasing again. Same deal. This one would be decreasing, because again, we're always reading it from left to right. Decreasing throughout the interval, except here where it levels off to 0. All right, that's close, except it's the opposite of what we want. So this one does level off to 0 in the middle, but it's increasing throughout, so it would be this graph. All right, so we're looking at a case where we have no extreme values, but it does seem that we have a point of inflection on the graph, which we're going to address more down the line, but any change in concavity leads to inflection within the graph. So this one is concave down, followed by concave up, It's just a question of how it bows itself, all right? So if it's bowing in an upward direction, then it's concave up. The reverse is concave down. So the moral of the story here is when you set your first derivative equal to 0 and solve and get a value, it may not be a relative extremum. It could be an inflection point, all right? So we can't just make the assumption that, okay, I took my derivative, set it equal to 0 and solve. My extreme values must be at these points. You have to do some sort of fleshing out of what is really going on at that point. And the sign chart analytically is so far the only way you would know how to do that. All right, so it kind of sucks, but that's how it goes. We do have something called the second derivative test for Extrema that will, where practical, give you the same answer. The problem is you sort of have to pick and choose your battles, because sometimes finding the second derivative in and of itself is just a nightmare. You don't want to do it. So you settle for doing the sign chart because you don't want to take the second derivative. Then there's some other cases, like in this situation, when I show you how to do this second derivative test, you'll be like, well, this is a polynomial function. It's very easy to find the second derivative. I'll do that for these kind of situations. All right, so you'll be able to kind of triage. So the next one, well, it's definitely not continuous and differentiable for every single value of x. It's continuous and differentiable on the interval, everything except for 0, right? Because there's a vertical asymptote there. On negative infinity to 0, union 0 to infinity. All right, so everywhere except for the 0. All right, so we keep that in mind, because if I go through the process of finding the derivative and my only and my only critical value is 0, I would dismiss it because it's not continuous there. Well, I would dismiss it as a possibility for being a relative extremum. All right, there's still value in knowing where the asymptotes are. And I'll show you what that looks like in a few minutes. All right, so I got to take the derivative of this. A little low D high action. Minus high D low over denominator squared, and away we go. So x squared minus 2x squared, that's going to give me a negative x squared. Then that's going to be minus 6x over x to the 4th. All right, so I'm going to set it equal to 0, which is the same idea. Generally, don't forget to set it equal to undefined for fractions, because I know that there's a denominator staring me right in the face. So negative x squared minus 6x equals 0. I would also look at x to the 4th equals 0. Bless you. So we get x equals 0, but that's a vertical asymptote. All right, so there's not going to be a relative extremum there because there's no graph there. It's still going to make its way into the sign chart, though. All right, so we still include discontinuities in the sign chart, all right, because they're natural boundaries created by the graph. All right, the other one, we do a little factoring, pull out a negative x, so x plus 6. And we get x equals 0 again, and x equals negative 6. So between the two, we don't have any unique critical values. Oh, we do have one unique critical value, and that would be x equals negative 6. The others are not unique, but they're both 0, bless you, and they're both vertical asymptotes anyway, or referring to the same vertical asymptote. So if there is a relative extremum, it would have to be at negative 6. So that's what the sign chart is going to help us figure out. So we have two values that we have to account for, the 0 and the negative 6. So x, f prime, conclusion, negative infinity going to negative 6. Stop at negative 6. Stop, take a look around. See what's going on at the negative 6. I'll put my lines in after the fact. -6 to 0, 0, stop, take a look around at 0, then 0, on to infinity. Draw some shaky lines. This chart, again, is going to help us make a determination of what's going on in this graph. Ultimately, we're going to learn how to sketch graphs of functions and their derivatives just by looking at the equation and the sign chart, all right? The function itself won't be as challenging as actually sketching the derivative. The derivative will be the greasy part, all right? So I know that there's a vertical asymptote going on at 0. So I really don't have to worry about at least 0 in and of itself. But I would like to know is, you know, because vertical asymptotes take on a few different forms. You know, so let's say I have 0 here, and I mean there is some horizontal asymptote there, so I can account for that also. I mean, am I talking about something like this, where it's concave up, you know, increasing on both sides, or maybe it's decreasing followed by increasing, or maybe decreasing followed by decreasing? It could be any combination of these 4 things, right? So if I needed to sketch this graph out, all I have is this. I know these are my possibilities. This is what I have to work with. But I don't know yet until I start evaluating derivatives, all right? The good news is, you look at this and you compare it to the previous problem, and you say, oh, wait, I got to plug numbers into this? Well, yes and no. If you look at the bottom, it's x to the 4th power, which means the bottom is going to be positive no matter what, which means it's irrelevant. All right, in determining the sign of my function, my derivative function, that bottom is not even factored into my thinking, because whatever I get on the top is going to drive the sign of the entire function. Right, so all I have to worry about is the top, so I just figure out a convenient number to plug in. And if you want, you can clean it up a little bit, because I know, for example, the factored form on the top is -x times x plus 6. So if I plug in something smaller than -6, that's going to make the outside coefficient, the -x, is going to make it positive, and the inside will be negative. Positive times negative will be negative. So I'm not even looking at I'm not looking at the numbers themselves. I'm just looking at the quality of those values. So again, the factored form of this is -x times x plus 6, depending on what type of number I plug in. Like, for example, if I plug in a -1, plug in a -1 on the outside, I'm going to get a positive number, right? Negative. On the inside, it's going to be a positive number, right? So positive times positive, we're looking at a positive value. And then if I plug in a number bigger than 0, like a +1, keep it simple, because whatever value you choose in this interval, assuming you set up your chart the correct way, whatever works for one value is going to work for them all. It doesn't matter what you choose. So choose the simplest value. Plug in a 1, positive number on the inside, negative on the outside. Positive times negative is negative. Right? These are little techniques where, you know, last year, maybe the year before, depending on the situation, where it's like, okay, cool, thanks for showing us that. I'll just do it on my calculator. But as you know by now, there's enough situations where you're sitting there without a calculator and you have to do these calculations, but in reality, they're not meant to be calculations. They're meant for you to kind of reason your way through it, right? And again, if you happen to know what the function looks like, that's even better. X plus 3 over x squared, it might be a tall order, but I mean, I've seen it before, so, you know, not for me, but you have enough experience and none of this stuff is overly challenging. But that's the thing, you don't have the experience yet. So once you have it, you'll look at this and say, oh, I know exactly what that looks like, and it'll be fine. All right. So I know I'm dealing with increasing then decreasing. All right. So around my vertical asymptote. So increasing followed by decreasing. So it would look something like this, right? Two upward facing asymptotes. I knew that because I've graphed enough rational functions where the bottom value is squared to know that that's how it plays out, right? When you do all those limit problems, you know, if you really do, if you're actually considering the graphs, every time you see something like this, you're like, okay, I got a vertical asymptote of 0. The little dude's coming in from the left, the little dude's coming in from the right. Oh, they're both going to positive infinity, all right? So that's just experience. That's how I would know that. But maybe I don't have the experience. My sign chart still tells me, all right? I pointed at the wrong thing. My sign chart still tells me. Now, around the -6, that's a continuous point. We're looking at something that is decreasing and then it's increasing. So if it has to be a relative max or a relative min at that location, it's decreasing followed by increasing. Which one is it? Relative min. Okay, so I just want to cross the T's and dot the I's here. Tell where it is increasing, okay, check. Decreasing, check. Identify any relative extrema, check. I threw in vertical asymptotes just for giggles. So, check plus. All right, so the sign chart is my answer, really. Aside from addressing the continuity and differentiability in great detail on the AP, I did what I needed to do, right? So no further comment is really required, right? Now, if you over abbreviate, then you want to write a formal statement, right? Because I've seen people go D R M I B A D, and I already know the graders for the College Board they're gonna play dumb, like, oh, D, all right, how do I know that means decreasing? It could mean derivative. Yeah, and I know it could mean, well, I can't say it out loud in class. It's a bad word. So that's the point. Yeah, dummy. We'll go with that. Yeah, that's precisely what I was thinking. All right. So your homework is number 3, and man, it looks like a really easy problem.